guys, so Mrs. Valdivia here, and I am going to be adding to the video that we did on chapter 5 called molecular shapes. So you'll be seeing me post that video on our file and along with this one. All right, so just to add on to that, we want to add for VSEPR, which is valence shell electron pair repulsion. Okay. And valence shell electron pair repulsion is known as VSEPR, and it's basically telling us that electrons want to be as far away from each other as possible. So electrons want to be as far away from each other as possible. Okay, so like I said, we kind of already covered this in our chapter 5, right? So we're just going to go ahead and add to those notes. What I wanted to add to it is our understanding of the difference between electronic structures and molecular geometries. So we have electronic structure, or the shape, I should say, and then we have the molecular one. You'll probably see the word shape as opposed to structure. Okay. So electronic structure is the arrangement of electrons around the central atom. So it counts all electron sets around the central atom. While the molecular structure only counts the shape formed by the atoms. It ignores the electrons, like the unshared electrons. So ignores unshared electrons. Now, that doesn't mean to say that the unshared electrons don't have a spot in it, because it does. And we're going to see that right now. We're going to use an example of NH3. Okay. So using NH3 as our example, we have nitrogen in the center, and it's going to be connected to our hydrogens. And it has one lone pair on the top. And we're going to do the same thing right over here. But now we're going to look at the differences that these shapes are creating. Okay, so an electronic structure, like I said, counts all of the electron sets. So we have an electron set occurring here, another one here, here, and here. So if we look at this, we have a total of 4 electron sets. And 4 electron sets is going to give us the shape of tetrahedral. And if I look at this one, it's only going to count the atoms, and it's going to ignore the unshared electrons right up here. So it's going to have this shape happening here. Now, they're not going to spread out because this is still here. It just doesn't count in the shape. So because it's there and we're not counting it as a nice little lobe or anything, it's kind of squished down. And that squishy down creates something similar to a shape that's like this, right? And that's a little pyramid-like shape, right? So it's a trigonal pyramidal. Okay. And this is going to be 3 electron sets and 1 lone pair. Okay, giving us that trigonal pyramidal. So I hope we kind of understand now the difference between an electronic structure and a molecular structure. One counts this as a connection, the whole lobe, and the other one does not count it as its collection, yet it still plays a part in the shape because it pushes these down. Okay? It repels them. All right, so now that we've done that, let's go ahead and just create a summary of our VSEPR shapes. We're going to create a little chart. Summary of VSEPR shapes. Right. And we're going to have the electron sets, the electron geometry, the model, bond sets, the lone pairs. You know what? I'm going to write pairs right up here. Lone pairs. The molecular geometry, and then this is going to be the name. I know I wrote kind of small here, and then the shape or an example. All right. You guys can make yours a lot bigger if you like. I'm just trying to fit it all here on this paper. This is what it's going to look like at the end right here. So this is what we're going to draw right there. Okay, so I'm going to draw this with you guys. We have the number of sets. We could have 2 sets, and the electron geometry is going to be linear. And the model is going to have the central atom, and that's going to be connected to 2 different sets. Let me use a different color here. Okay. So the number of bond sets on the central atom is 2. The number of lone pairs on the central atom is 0. The molecular geometry name for this is linear. It creates a straight line 180 degrees. And the example we're going to use is carbon dioxide with the 2 double bonds. All right, and let's go into another one. Let's go into 2 bond sets with an electron geometry of, no, that one's under tetrahedral. So we'll go into 3 sets. We're going to do trigonal planar. Trigonal planar. And let's go ahead and draw. We're going to start with our central atom. And our central atom is going to be connected to 3 other atoms, or 3 electron sets. So this is 3 bond sets, 0 lone pairs. The shape is going to remain as trigonal planar. And the example is CHH. I forgot what the name of this one is. And that's supposed to be an H right there. That's connected. Single bond to an H. Single bond, by the way. I know it looks like a double, but that is a single bond. And our electrons there. All right, the next one we're going to do is the tetrahedral. And this is where things are going to get a bit more interesting right here. So in our tetrahedral, we have our central atom, and it's going to be connected to 4 other atoms. Make it actually look connected there. All right, so if we have 4 bond sets with 0 lone pairs, then our shape here is going to be tetrahedral. And if we have 3 bond sets with 1 lone pair, the shape is going to be trigonal pyramidal. And if we have 2 bond sets with 2 lone pairs, then our shape is going to be bent. And let's give our examples. For the tetrahedral, it's going to be carbon connected to 4 hydrogens, which is methane. For the trigonal planar, is going to be our ammonium. Okay, connected there. And the bent is going to be our H2O, or water. Right here, and you could create that bent-like structure. Now I realize that I skipped one for our 3 electron sets right here, because what if this is a single pair, a single lone pair, as opposed to an actual atom? So we could have 2 bond sets with 1 lone pair right up here, and that 2 to 1 is going to also give us a bent shape. And that bent shape is, example, it's going to be our nitrogen single bonded to an oxygen and double bonded to another oxygen, so NO2. Right, so something like that, where this oxygen ends up with a negative charge right here. All right, so that is the summary of our VSEPR shape. So we're going to go into the other thing we've talked about, which was hybridization. So let's go ahead and go into that now. Hybridization. Remember, you can pause the video to continue taking the notes. Okay, so going into hybridization, that basically means that your electron jumps between sublevels when excited. Okay, so let's go ahead and give our example of that happening. We're going to look at carbon. Yeah, let's make a little chart. This symbolizes that energy increases. Okay, so energy is increasing as you go up. Okay. And this is going to symbolize our ground state. So we're going to have a 1s, a 2s, and then a 2p right here. And we're going to draw our electrons. So carbon has 6 electrons. It's going to have 1, 2, 3, 4, 5, 6 electrons in it right there. Now, when it gets excited, what's going to happen is that one of the electrons from the lower sublevel is going to jump up to the next highest sublevel. So this symbolizes the electron being excited. And it gets excited when it absorbs energy, right? So it takes in energy and it gets excited. Right? Now, this is going to create a process known as hybridization. And now what we're going to see our 1s, but instead of seeing a 2s or a 2p, you're going to see something kind of in the middle of these, and it's going to be 1, 2, 3, 4, and it's going to be called an sp3, made of 1s and 3p sublevels. And this is now just one hybrid orbital. And so when this hybridization happens, this is what's allowing some of the expanded octets that we've seen. Okay, so we're going to have 1, 2, 3, 4, 5, 6. And that is what allows carbon to actually make 4 bonds as opposed to just 2 bonds, right? It's that expanded octet. Actually, no, this is a normal octet, but it allows it to make it because of that hybridization. And like I said, you'll see sulfurs and phosphorus, they all make expanded octets because it goes through hybridization. And that's when we're able to get things above tetrahedral, when we start going into octahedrals and whatnot. We should just be able to explain that they go through hybridization and they combine in our orbitals, like an sp3 or an sp2. All right, you guys, now let's go into polar bonds. So we're going to talk now into the polarity of our bonds. So in polar bonds, atoms are not sharing electrons evenly. Okay. There's different charges on the molecule. This creates different charges on our molecule. And we've seen that when we calculated formal charge. Okay. And the reason, so the why, is electronegativity. And do we remember which atom is the most electronegative? Fluorine, right? So that's the tendency of an atom to attract electrons towards itself. And we said fluorine atom is the most electronegative. And the value is 4.0. So, and when you see me write electronegativity, you might actually see me write electron and negative sign like that. So the value, the electronegativity value for fluorine is 4.0. That's the highest. Okay, that means fluorine can attract the electron from any of the other elements. All right, so let's look at an example, hydrogen and fluorine. Okay, so fluorine has 7 valence electrons. It's going to share 1 from this hydrogen, but is it going to share these electrons equally? The answer is no. So what you're going to see is that the electrons are going to pass through hydrogen very, very fast, but they're going to spend a lot of time next to fluorine. And that's because fluorine has all the electrons around it due to its electronegativity. So it's going to have a negative dipole, while hydrogen is going to have a positive dipole. So these right here, remember, they're called dipoles. Okay, so this is a positive end and negative end. And the way it travels is that this is the most positive side. This is called the dipole moment, and it moves to the more negative side. Okay, so this is a dipole moment. Okay. And it shows where the electrons are at. So it shows electron travel. Right? Where are the electrons moving? In this case, they're moving towards the fluorine. Now we have bonds that do share electrons evenly, and those bonds have a different name. They're called polar covalent bonds. So bonds that share electrons evenly polar covalent bonds. Okay. So this is what we're going to see now. If we're going to draw the different types of bonds that we've been introduced, we're going to have a covalent bond. We're going to have a polar covalent. And we're going to have an ionic. Okay. So our covalent bond is going to be made up of nonmetals and nonmetals. So we're going to have nonmetal plus nonmetal. And actually, let's write that down for all of them. Polar covalent is also nonmetal plus nonmetal. And ionic bonds are metal plus nonmetal. All right. Sorry, and the bonds that share electrons evenly, they're just called covalent bonds. They're not called polar covalent bonds. Please delete the polar right there. It's just a covalent bond. All right, that's because they're evenly shared. The ones that are not evenly shared are called our polar covalent bonds. So those are our polar bonds right up there. Fix that bit of information before I give you more incorrect stuff. All right, so if we start looking at this, 0.5, and this is a 1.9. Okay, that's 0.5 and 1.9, and this leads all the way to our 4.0. We're going to look at the polarity of our items. So from here to less than 0.5 is going to be a covalent bond. From here to here is going to be our polar covalent bond, and from here to here is now going to be an ionic bond. Right? So what does this mean? This is shared evenly shared electrons. This is unevenly shared. And these electrons are not even shared, they're just transferred. So there's no sharing when it comes to an ionic bond. Okay. Let's do an example. Okay. If I did carbon monoxide, which is just CO, and I wanted to look at the polar bonds in this molecule itself, right? How are we going to figure that out? Well, there's the mathematical way, which is we're going to look at an electronegativity chart, and we're going to notice that carbon has an electronegativity value of 2.5, and oxygen has an electronegativity value of 3.5. So we're going to take the absolute value of those two subtracted, and you're going to get a value of 1.0. 1.0 lies right here in this polar covalent area. So that means that this is a polar covalent bond. Okay. So when I draw this, I could show that the bond here between oxygen and carbon, right, that the dipole moment flows that way from the positive end to the negative end, creating that dipole for it. Now, if I did carbon dioxide, it's still going to be polar covalent in the individual charges. So you're going to have carbon. Actually, this should have been a double bond, so I'm going to erase one of those. And oxygen. And we're still going to have the same 1.0 and 1.0. So therefore, the dipole is going to show like this. And going like that. That's the dipole. more negatives, and the positive dipole right here. But what does that do? Okay, the difference here now is we have in this area all our electrons flowing to one side only, right? So this whole molecule is a polar molecule. However, in this one, it's different now because in this one, we have electrons going here, but at the same time, flowing there. And it's creating an even distribution. This is symmetrical. And this one is asymmetrical. So therefore, this molecule is a covalent molecule. Okay. This linear shape is a covalent molecule because the electrons are shared or distributed equally throughout the entire molecule. It creates that symmetry. On this part right here, though, it's asymmetrical, so it's going to be a polar molecule, right? So we just learned shapes. We learned polarity of these shapes, and we have to know what the shape is in order to be able to figure out the polarity, because we could see, is it going to be symmetrical distribution or are we going to have an asymmetrical distribution for it? All right, so when you're doing your work, keep those things in mind. First, figure out the shapes. After you figure out the shapes, start looking at the polarity of your molecules. All right, you guys, hope this was helpful. Have a nice one.